All right. So, hello everyone, and welcome to the webinar series on robotics for rehabilitation and elderly care. So, this is a seminar series as part of IIT Gandhinagar Mechanical Engineering, Cognitive Science, and part of Spark project. We are trying to conduct a series of webinar in the said area. My name is Vineet Vashisht, and I am assistant professor at IIT Gandhinagar. Today, we will have our third webinar on the topic robotics for assessment and training of dynamic balance during walking by Professor Zlatko Matjačić. Before we get started, I just want to make a quick note that during the talk, you might have a number of questions. So we will appreciate if you can just write those questions in the question and answer section. So in the interest of time, the panelist will take your question at certain interval. And of course, I think otherwise we will talk at the end of the seminar. So let's get started. So I will just briefly introduce Professor Zlatko. He did his PhD in electrical engineering from University of I think I may have some pronunciation issue, but Ljubljana, and he's currently a full professor in biomechanics at the same university. And side by side, he's also heading a research and development unit at University Rehabilitation Institute, Republic of Slovenia. He has published a lot in the same area, and his main research area is in human motion analysis and synthesis, biomechanics, and rehabilitation robotics. Among the various journal publication, I think one of the key highlight is he has around 11 international patents, out of which 2 products have been out, one on balance trainer and walking balance training device. He kind of also have worked on upper extremity movement for neurorehabilitation as well as on walking. And his main research focus is on transferring the basic science into viable practical approaches. And I think that is very relevant from various students' perspective and various kind of research work that are going in various universities. And we are kind of really privileged to have you, Professor Zlatko, in front of us to present some of your research findings and I think share the knowledge with us. So with any further ado, I will like you to take your session.
Thank you, Vineet. Thank you for this kind introduction. I hope you're hearing me. Everything is working fine.
Yes.
Just to have quick feedback. Okay, great. So first of all, I would like to thank to Professor Vasista to invite me to give talk in this series of webinars. I must say that the company that I'm in is very distinguished. So Professor Agrawal was the first speaker, as I saw. So I hope that I will live up to your expectations and give you an overview of, let's say, our last 5 years of our research that we did, mainly on the topic of dynamic balancing during walking and this associated robotics devices. So let me see. I hope that. Okay, it takes some time. That's a problem. Or right. So balancing in bipeds or bipedal locomotion. So as you know that we bipeds have evolved to stand up our hind limbs, which gave us some evolutionary advantages, but on the other hand, it gave us a little bit of challenges that we need to tackle. And one of those challenges is related to maintenance of balance while being on 2 feet. So if we can look upon that from different perspectives, but our perspective is from the perspective of rehabilitation, restoring balance in people after different neurological diseases and disorders. And related to gait balance instabilities which may occur, those can be either extrinsic or intrinsic. So extrinsic causes are related to slips, trips, pushes, and different situations that happen unexpectedly to us. And also, when we talk about certain neurological diseases, disorders, there is also the intrinsic factor which originates from sensory motor fusion, basically meaning that we perceive our surrounding and our, let's say, biomechanical aspects of interaction with surroundings in a way which is not correct. So either the perturbation is of external or internal origin, we need to exercise appropriate corrective actions as a response to these perturbations. And of course, balancing in bipeds is challenging because of this picture somehow nicely illustrates that, showing that our contact with the ground is rather limited, small. Here are certain variables, biomechanical variables that we can control, like center of pressure, ground reaction forces. And here is our main controlled variable, center of mass. And basically maintaining a balance relates to keeping this center of mass in a way which prevents us from falling. So it's very difficult to give appropriate definition of balance, but let's say that this one is the one which is the most relevant in context of rehabilitation. So, okay. So now coming to, let's say, more biomechanical description of the problem or the task in hand. And what you see here on the right-hand side is actually a couple of figures from Goswami, who use that in synthesis of bipedal robotics. And basically what we see here is, let's say, humanoid structure, the center of mass of this structure. And then here we see the contact with the ground. So the foot is in contact with the ground. Here is the instantaneous center of pressure and ground reaction force. So we need to recognize there are two external forces acting on our body. One is gravity, the other is ground reaction force. So we don't have much influence on the gravity. So the only thing we can control is the center of pressure and ground reaction force. And if we look at the change in linear momentum is the sum of these two external forces, while the change of the angular momentum is that one needs to be defined around certain points. So if we define it around the center of mass, then this equation governs the change of the angular momentum. And basically, if you like mathematical definition, what we would like to do, we would like to keep the changes of linear and angular momentum during walking as small as possible. So how do we do that? And this is something which we do imminently in bipedal walking. So we cannot distinguish really the walking mechanism from dynamic balancing aspect of it. And like I said, whether or not these are external pushes or internal origins of perturbations, in healthy individuals, so now we talk about the humans, we don't talk about robots here. The humans, what we do, we have several strategies at our disposal. And we somehow divided those strategies in two big categories. One is in-place strategy, and the other is stepping strategy. The in-place strategy actually consists of modulation of center of pressure and ground reaction force under the leg in stance. That means that during walking, the periods of double stance are quite small. So most of the time we support ourselves during single leg stance. So we can confront different perturbations either on already on the leg which is in stance in the moment, or we can do that by taking additional step or another step. So in order to visualize a bit more, that a little bit in more detail, here we have these different strategies visualized. So here we have a situation, if you like, unperturbed walking, where we have a center of pressure which travels from the heel to the toes, sort of following the center of mass. So for example, if there is an external push to the pelvis, then what we could do, we could exert additional plantar flexion torque, meaning that the center of pressure will be displaced further in front, and this will then create situation with ground reaction force, which will be acting to decelerate this movement, which was originated by the push. If this is not enough, or if the push is too strong, what we could do, we could resort to hip strategy, or even more general, to inertial strategy, meaning that we would be exerting torques in the joints which are above the ankle, but the most prominent joint where we do that is in hip. So that's why also this inertial strategy is named as a hip strategy. And depending on further on the strength of this perturbation, or when in the gait cycle the perturbation occurred, what we could do, we could counteract this perturbation in our next step, meaning that our next step is longer, wider, or depending on the direction of that perturbation. So this was general overview to give you a perspective, and now I will go to give you an overview of our work in this area. So the first thing is what we did. We developed a robot which is capable of delivering or imposing perturbations during overground walking. So this paper is about this robot. And here in this video, you will see, so this is an older video that was done in the framework of the European project, Seminar Framework Project Balance. And we developed this robot. So it's on, you see, this is a mobile platform, and 6 degrees of freedom mechanism, which embraces standing pelvis. And we can apply perturbations on the pelvis in different directions of the transversal plane. Here we see my colleague Matjačić walking in the machine, and another colleague is steering the mobile platform. And now you can see here the perturbations which occur during this overground walking in different directions. So this was one of our first devices for exerting the perturbations. This was for the overground walking. We developed a twin device, which is used for treadmill walking. And here you will now see my colleague walking on a treadmill, and the perturbations occurring in the forward direction, and of course his reaction, and then to the backward direction that was not so visible. Then also the perturbations around the vertical axis. And then there is the perturbation which is termed inward perturbation, which basically occurs with the foot contacting the ground and the perturbation being directed in medial direction. So here I'm demonstrating the movement also of the vertical degrees of freedom. So this device is basically admittance controlled machine, and we control it in a way that the machine is most of the time transparent. And when we want to elicit a balancing response, we apply perturbation in different directions. Okay, so the machine, actually this robot is placed around the instrumented treadmill, with which we can measure ground reaction forces and center of pressure, the instantaneous center of pressure ground reaction forces, while the center of mass is estimated through the movement of the pelvis link. And what we did in several studies, we first looked into how intact subjects, or if you like, control subjects, what are the strategies and what way the people react to these perturbations. What I need to mention also is that, of course, this is a not new field. There are many different studies which has been published, and a lot of people looked into this. Our studies actually distinguish from the existing body of literature in the following aspect, and that is that we looked into the responses at very slow walking, so at very low walking speeds. Most of the studies has been done at normal walking speeds, which is in, if you like, intact humans around 1.2 meters per second, while we did it at considerably slower walking. So this is one study. Another study is this one, and now I will now show you or guide you through some of the like strategies used by intact control subjects after perturbations in the frontal plane. So to illustrate what is going on during unperturbed walking, here we see, so this is like a left foot step and right foot step. So here is the center of pressure movement during walking. And what we see here is the alternating movement of the center of mass position. So the center of pressure of the leg, which comes into the next stance. So the difference between the two, according to the inverted pendulum modulum, inverted pendulum, is actually proportional to the lateral ground reaction force, which controls the movement of center of mass, right? So this is the case in the unperturbed walking at all speeds of walking. So what we see here are the responses to the invert perturbations. So the invert perturbation is when, for example, here we have a right leg entering the stance, and at that time, the BART device applies push in the medial direction. So what we see here are the responses to 3 different walking speeds. So let's take a look first at speed 0.8 meters per second, which is closer to the, let's say, normal walking speed. So in the previous slide, I have shown you the movement of the center of pressure. So we have center of pressure, right leg, left leg, right leg, left leg. And here we have center of mass movement. So the green line here is the unperturbed walking, and then the 3 further lines show perturbations at the different perturbation strengths. So basically, when we enter the stance, here is the time when the perturbation acts. What we don't do much on the standing leg, but what we do, we modulate the position of the ensuing step with the other leg, and depending on the perturbation level, you can see that also this step width is progressively wider. That has influence on the ground reaction force. So, like I said before, center of pressure minus center of mass determines the ground reaction force. And this is the main mechanism, so the stepping response in the mediolateral plane. If we look also what's going on in the sagittal plane or the anterior-posterior plane of movement, what we can see, there are some changes also in the center of pressure there, and consequently ground reaction force. And this is mainly has to do with the fact that we shorten our stance. If we now go to the bit slower walking, what you can see that at walking speed 0.6, This is quite similar to 0.8. And if we look at 0.4, again, we see the similarity. So as far as the inward perturbations are concerned, apart from there are some changes, there are some modest changes, but more or less there is the only one strategy, and this is stepping strategy. And if we look at the center of mass peak excursions, so here is in unperturbed walking, and then progressively as the perturbation strength increases, we have increased center of mass displacements, and this is for 0.4, 0.6, 0.8 meters per second. This is in medial lateral direction. And in the anterior posterior direction, there are also some, if you like, retardation of movement, or after the perturbation is applied. So the response is such that the center of mass in the anterior posterior direction is a little bit retarded, but like I said, it's quite similar for different walking speeds. If you look at the step lengths, what we see is that at 0.8 meter per second, what we see that the response is such that the next step length is shortened, and this actually is shortened progressively more with the progressing magnitude of perturbation. It's similar situation at 0.6 and 0.4, but you see that here actually the step length, so this negative step length actually means that a person does not really progress much with the leg in swing, but quite soon it puts the leg on the ground. The step width, we talked about that a couple of slides before, and you can see that there is an increase in step width for all three walking speeds, and progressively more with progressive magnitude of perturbation, and the step time is decreasing progressively. Okay, so if you look at the ground reaction impulse, so if we integrate, if you like, the ground reaction impulse for the instance period, so the period when the leg was in stance, what you see there is actually that this ground reaction force impulse is decreasing, and this is mainly due to the fact that the time of the leg in stance is also decreased. And this is quite similar for different walking speeds. And on the other hand, this impulse increases when the next leg enters the stance, which is, like we said, it's progressively more, it's wider step, and also proportionally there is also this impulse which is bigger. So this was as far as the inward perturbations were concerned. But if we look at the outward perturbations, we see that the situation is a bit different. So first let's see again what happens when the perturbation outwards, it's again right leg entering the stance, but in this case the BART pushes pelvis to the right, or if you like, into the lateral direction. Now, and this happens here. So before here, in the gait cycle from -50 to 0, this is the unperturbed walking. Here is when the perturbation occurs. And then after this perturbation occurred, we then see what is going on here. And first thing that we see is that the center of pressure is displaced more laterally. And this is again, it's displaced laterally as far as possible, regardless of the magnitude of perturbation. And basically, this has to do with the fact that the width of the human foot is quite narrow. So this is the first thing. And concomitant to that, what also we can see is that the ground reaction force and lateral ground reaction force is also decreased. In anterior-posterior direction, nothing much is going on. So the main response comes when the left leg enters the stance. And again, now depending on the magnitude of perturbation, this step width is more or less to the lateral side. So this leg, instead of landing here, it will land here, here, and here, producing actually also the cross step for the grade, so for the biggest level of perturbation, so 15% of body weight. So this is the stepping response. If now we look into the responses at a bit slower walking speed, 0.6, we see that here we see even a bit more the displacement of center of pressure under the leg in stance, so the medial lateral ankle response. But what we see here also is that in the ground reaction force, we can see here some sort of reflex activity. So the medial ground reaction force immediately after or like 150 milliseconds after the perturbation ceased, there is this increase which acts in a way, so it acts in a way to decelerate the movement of center of mass. And depending on the perturbation magnitude, there is also a little bit of modulation of this response. But we also see in the anterior-posterior direction that is something going on, and that is that the center of pressure is displaced quite rapidly toward the front of the foot. And this is the most visible for the strongest perturbation. And now if you look at what's going on at the slowest walking speed, okay, so here, so there is something going on already during the stance period, instance period, but again, most of the response comes for the highest perturbation, again from the stepping response. But at the slowest walking speed, what we see here is that here is the change in the ankle medial lateral strategy, so displacement of center of pressure. But here we see that the main response comes in this reflex-like activity of the ground reaction modulation. This is predominantly under the control of the hip abductors. Here we see also much pronounced displacement of center of pressure, and also quite a bit of ground reaction force which decelerate movement in the sagittal plane. And actually the effect of the perturbation is actually contained already in the instance period of walking. So in the stepping period, so when the left leg enters the next stance, almost nothing is going on here. So the whole response or the perturbation was contained in the instance period of walking. So this is clearly different from the inward perturbations, right? And now if we look that into across all the subjects, so we see here that the center of mass displacement is for different speeds, it increases with the increasing magnitude of perturbation. And here we see much more pronounced center of mass retardation in anterior posterior plane, which is much more pronounced for the slower walking speed. Step lengths, okay, we can skip that. It's not so. If we look at the ground reaction force, these impulses, what is interesting to see is this. So for the outward perturbation, so here we see, depending on the perturbation magnitude, there is a considerable increase of this ground reaction force impulse, which is not really the case for the higher walking speeds. For the instance period and for the stepping period, we see this can be seen that there's almost no difference for different perturbation magnitudes, while at higher walking speeds we see this instance strategy. Okay, so is there any question? I can see that somebody is right. Okay. Okay.
Yeah.
So
yeah, Professor.
Right. Okay. Okay. So the center of mass. Yeah, I understood the question. The center of mass is tracked by the movement of the BART. So we keep track of moving of this pelvic link, and then we say that especially for the very slow walking, even perturbed walking, it has been shown that the approximation of center of mass with the movement of pelvis is quite okay. So this is how we track the center of mass movement. Okay, I hope I answered this question. So,
and yeah, Professor, so I have a quick question. So,
yes.
If I'm correct, so force perturbation is being applying during stance phase of the gait, right? Or
yes.
just the initial? Okay.
Yes, when in the beginning of the stance phase.
Okay, so is there any reason like we targeting that phase, like not during the mid stance or?
Yeah. Okay, good question. We actually did both. I have shown. I think you can appreciate that even now the results are quite comprehensive. Now, if I wanted to mix up also with the responses to perturbations occurring in the later phase of the stance phase, but the reason why we are looking at in the beginning of the stance phase is because that means that at the slowest walking speed, that means that there is more time which needs to lapse before the leg in swing will be able to land and deliver the stepping response. So it is much more pronounced, or the need for instance response is much greater if this happens immediately in the beginning of the stance. But we looked into the responses also in the mid stance and at the end of the stance phase, and then you have a mixture of responses. When it is in the mid stance, you see a combination of instance and stepping, and when it is at the end of the stance phase, then basically it's only stepping response.
Yeah, thank you. And so we have one more question.
Yes.
So Chinmay asks, what is the reason for walking speed of 0.2, 0.4, and 0.6? Normal gait has approximately 1 meter per second, 1.1 meter per second.
Right. Good question. So the reason is, actually, I should have said that. So thank you for this question. This will be apparent to you when we go to the responses in hemiparetic subjects. So if we look at the people after stroke, even after they are let's say when they finish rehabilitation, the literature states that their walking speed at discharge is around 0.4 meter per second. And actually the ambulatory subjects, they walk with speeds from 0.4 to 0.8. So while these responses may not be so relevant for the control healthy subjects, they are very relevant for the hemiparetic subjects. Or if you like, there's another reason for that, and that is linked to the fact that most of the maneuvers that we do during walking, so when we change direction of walking, or when we slow down, or if you like, if we walk at our homes we don't walk at speed 1.2 meter per second. We walk slowly, we change directions and so on. So if there is some unexpected perturbation occurring in these circumstances, then the dynamic responses are more relevant at lower walking speeds. Okay, there are more questions?
So yeah, we have one more question. So do you also check the stability quantitatively while doing the experiment? If so, please, can you comment on how to quantify the stability?
So you mean online, like during walking?
Yes.
Yeah. Okay. So what I have shown so far, this is all analysis which has been done after the offline analysis. Online, I think it's quite tricky. It's quite difficult because what you need to do, you need to track the movement of or center of pressure, center of mass. And even if you do that, then you need to rely on some sort of a model. Like if you use inverted pendulum model, this is quite okay for higher walking speeds. So then people used like margin of stability related to the movement of XCOM. So the center of mass, which is augmented with the velocity kind of measure. So this is what people did. but this is something which we didn't do in our work, what I presented so far.
Yeah, so thanks, Professor. So you can proceed with the talk.
Okay, thank you. So, I have shown you so far what's going on in the control subject, and now I will show you a study on dynamic balancing responses, again into neurological intact subjects, but now we looked more into 0.4 meter per second, and we looked only into outward perturbation. Clearly, presenting before these perturbations, these are the most interesting ones, because we wanted to see a little bit more what is going on there. So what you see here is again, my colleague Matjačić, and here is the perturbation when he enters a stance with the right leg. And what you saw was that everything was done during the instance period. So maybe I can run this again. So please observe this. So what happens now is, okay, there is some movement of the swing leg, lateral movement, but the next stepping location is exactly the same as during the unperturbed walking. So we were interested in seeing what exactly is going on and in what way this coupling of the sagittal and frontal plane, how does that work? So here is actually our hypothesis. This was the hypothesis of our study. So here is the unperturbed walking, the situation in unperturbed walking. So here we see the center of mass, center of pressure under the foot, the vertical ground reaction force, and the lateral ground reaction force. So when the perturbation now occurs into the outward direction, so to the right, what happens is that or let's put it this way. So what we thought is going on is the following. So the center of pressure needs to be displaced as far as possible laterally. And why is that so? That is so because what we need to do here, if we want to contain this perturbation during the instance period, we need to generate quite substantial lateral component of the ground reaction force. But of course, if we increase that, that means that multiplied by this rather long moment arm, this will have effect on the change in the angular momentum. So what we would expect is that there would be also concomitant change in the vertical ground reaction force, and this increase should be such to be able to counteract this change in the angular momentum. So basically what we want to do, if you remember slide number 2 or number 3, we want to control the rate of change of angular momentum. And if we look at the human foot, this is the top view. If we what we could do to facilitate, so if this happens at the initial foot contact, so this the space to displace this center of pressure is rather small, right? But if we increased also center of pressure in the anterior posterior direction, then we get a little bit more space also for the lateral displacement of the center of pressure. But if this is so, if this is really the mechanism, that means that then the center of pressure in the sagittal plane would be displaced forward. And now we said we would like to increase the vertical ground reaction force. If the vertical ground reaction force is increased and also the center of pressure is increased, then now we see quite substantial external moment which acts around the center of mass, which will have effect on changing the angular momentum in the sagittal plane, trying to rotate let's say the composite angular momentum of whole body in the counterclockwise direction. And in order to fight against that, we need to increase the ground reaction force. Now, looking into facing to the opposite of the plane of progression, in order to sort of balance this change, right? And here we see the kinematics and kinetics. So this is now, these are the group averages. We did a similar experiment in 12 healthy control subjects. And here what we see, this is the black lines show the unperturbed walking, and the red line shows the perturbed walking. And here are the standard deviations for the whole group. So what we see here is that after the perturbation, the outward perturbation commences, we see the expected displacement of center of mass in the frontal plane. But we also see the retardation of movement of center of mass in the sagittal plane, which is sort of in agreement with the slide that I have shown you before. And we see here the center of mass in the vertical direction. We see in the vertical displacement of center of mass in this instance period. Now, if we look at the ground reaction forces, so we again see here this reflex-like increase for short period of time of ground reaction force in the frontal plane. This is accompanied with also the short ground reaction force impulse increase in the sagittal plane and in the vertical direction. Now, but we said that this ground reaction force would be much bigger, right? Or we would expect it to be much bigger. But of course, this cannot be the case. Why this cannot be the case? If this ground reaction force was bigger, then one thing is that the center of mass displacement goes up, but another thing is that we would have we would have knee going into hyperextension, and this is something which, of course, we humans are not very keen on doing. This would have counterproductive influence. So what we see here, the concomitant increase in ground reaction force X, Y, and Z, but then we see decrease in the vertical ground reaction force, and this has to do with bringing back the vertical center of mass. So, and looking into this part of our hypothesis, so what we see here we see the center of pressure displacement relative to the ankle marker placed at the malleoli. So we indeed see the increase of lateral center of pressure displacement, but we also see the forward center of pressure displacement. So showing that indeed this is the mechanism. And if we now look at the changes of angular momenta, and in the instance period, so this is the one in the around the x axis. So basically, this is in the sagittal plane. So we see the increase, which follows then by the decrease, and this is all in the instance period. And then regarding the frontal plane, so there is the inevitable increase in change of angular momentum in the beginning of the instance period, which is related actually to this peak here. Okay, and then in the remainder of the instance period, you see the decrease of this angular momenta. So basically, angular momenta in the sagittal and frontal plane are back to the levels of unperturbed walking. And then in the stepping period, we see almost no changes. So maybe we can pause here for a second. And if there are any questions, so yes, please. I see there should be a question.
Yeah. So Karthik asks, so what kind of sensor is used to measure the pressure distribution in the foot? Like, is it a sensor placed beneath treadmill or? Yeah,
this treadmill is instrumented. So under the treadmill there are three-axis force sensors. And from those force sensors, we measure the ground reaction force and the center of pressure. Maybe I should add, just to summarize this part, is that so what can be seen here from this study is that the dynamic balancing responses at very low speeds, when the perturbation occur at the heel strike or in the beginning of the gait cycle, actually require quite elaborated response. And this response is not limited only to the frontal plane, but as we could see, it's also to the sagittal plane, to the vertical axis. And also the one previous study have shown that it's also, they're basically responses, very, very comprehensive response, which is something which we could not expect from most of the post-stroke subjects to be capable of doing. So now I will go to this part of my talk, which relates to the assessment of dynamic balancing responses in post-stroke subjects.
So, Professor, we have a quick question.
Okay.
Sorry to interruption. So,
no, please.
So in the video, the system seems to restrict the free movement of hands in forward direction. So how does this affect the center of mass? One of the attendees asked this question.
So what do you mean? In what way it restricts? So the people were asked to have their arms folded on their chest, right? In order to, but here this particular experiment was done with very carefully selected perturbation parameters. So the perturbation there was 10% of body weight, and this was actually, we saw in previous studies that this is the magnitude which enables people to do their response or their instance response. And if you were observant of the video, you saw that the only the leg in swing actually moved. So there was the only inertial movement, while the trunk didn't move much, or the arms not. But if we increase the magnitude of perturbation, of course, then we would see also the movement of arms and trunk.
Thanks, Professor.
Okay. So when we talk about balance after stroke, then we need to first say what is the walking after stroke, what we see there. So the post-stroke subjects typically display asymmetry in weight bearing, asymmetry spatiotemporal parameters, and so on. And especially in frontal plane, their balancing abilities may be quite poor. So we wanted to understand the specific aspects of balancing in post-stroke population, to understand the particular deficiencies, and to tailor subject-specific approaches for rehabilitation. So this is quite recent study. We published this in Journal of Neuroengineering Rehabilitation. I will walk you through the study. Here in this study, we assessed first dynamic balancing responses in control population in 43 subjects. And then we assessed in exactly the same conditions in subacute stroke subjects. These subjects have finished rehabilitation. There were 41 of them, 22 right hemiparesis and 19 left hemiparesis. And inclusion criteria were functional ambulation category 5 or 6. That means that these subjects were independent walkers. That means that they could walk independently without help of anybody, without help of assistive devices, without help of canes, crutches, and so on. So they were considered as independent walkers. Meaning that according to the literature, the independent walkers should be much less prone to falling than non-ambulatory post-stroke walkers, right? So here again, we looked into slow walking because we saw that slow walking is most demanding in terms of balancing responses. The perturbation amplitude was 10% and 150 milliseconds perturbation direction. We perturbed subjects in forward, backward, left, and right directions, 7 repetitions, and we perturbed them at heel contact of left or right leg. So for post-stroke subject, that meant on hemiparetic and non-hemiparetic leg. And if we look now for the outward perturbations, so these are perturbations of the left study I have shown. So in healthy participants, we see here this ground reaction force impulse. and this is symmetrical. So if you look at this response, so to the perturbation on the left or right leg, here is the symmetry line, and we see that the responses are quite symmetrical. So the ankle response, this is the response under the stance leg in the center of pressure displacement. And if we look now at the typical, or not typical, the hemiparetic participants, which was right-hand sided. So when, with the right side hemiparesis, so when the perturbation occurred on the left side, we see quite similar response to control subject. But when it happened on the paretic extremity, we don't see the instance response, we see quite a substantial stepping response. And now looking into the symmetry plots, that means that their responses are quite far from the symmetry line. So now we look at so these are the responses to forward perturbation, again on the amputated, or not amputated, the paretic and non-paretic. We also did this study in amputees, so that's my mistake. So what we see here is that the healthy representatives, they counteract perturbation during the instance period by appropriately modulating ground reaction force and the center of pressure. And here is the stroke representative, right hemiparesis, and he does similar as far as the perturbation on the left leg is concerned. The perturbation on the right leg, there is the symmetrical response for the healthy control, and here we see the stepping response for the paretic subject. So here we see the responses of all of them. Here we show the center of mass in the anterior-posterior direction. And you see that, so majority, of course, of healthy controls are here in this ellipse. And half of the hemiparetic subjects are also within this ellipse, and approximately half of them are outside. And if we then looked into the change in the maximal displacement of center of mass, we see that this outside group, so the group which is outside this normative ellipse, they show the significantly higher displacement of center of mass. And we also see that the strategy is quite different. So the healthy controls, they do it in the instance. So with the modulation of ground reaction force in the instance phase. The inside group, so we divided them into groups. This hemiparetic subject, the inside group is kind of similar. In the outside group, is a different kind of response. And here we see in the stepping period. And in the paretic leg, of course, this is much more pronounced as for the unparetic leg. And in backward direction, we see kind of similar situation. So half of the subjects inside the ellipse, half of outside, and not going into too much details again here. If we look at the inward perturbations, so these are the inward perturbations, here we see that the majority of the subjects, their responses were inside the normative. This can be also see here from the representative plots, and we can also see here from the center of mass, the ground reaction force displays a change in instance and stepping. We don't see changes in the groups, meaning that the inward perturbations actually are the easiest ones to cope with for the ambulatory post-stroke subjects. If we look at the perturbations in the outward direction, we again see similar as for the sagittal plane perturbations. Half of the subjects they are within the control group, and the other half is outside. And we again see the significant changes in the center of mass displacements and in the strategy that is used. So to summarize these observations, even though the subjects are considered for the clinicians to be equal, meaning that they are all ambulatory, we see that with this particular assessment at slow walking speed, we see that there is directional specificity of dynamic balance deficiencies and dynamic balance responses. And again, and also, so not all the subjects that were inside this normal ellipse, they were not the same subjects for different perturbation directions. That again means that what we need to do when we talk about rehabilitation, or if we want to improve balancing of these subjects, this needs to be done. This needs to be done on a subject-specific way, meaning that we need to first see in which directions we have deficiencies, and then we also should tailor the perturbation program, perturbation-based training, which is more pronounced in those directions. So this is, now there is a time for another question, if there is a question. If there are no questions, I will move on.
So we have a question.
Okay.
So from one of the attendees named Vikram. So Vikram asks, so how much perturbation forces are given? And are all subjects given the perturbations with same forces, or do we tailor them for specific subjects?
Yes.
And what is the criteria for choosing the magnitude?
Okay, it's similar as before. So it's 10% of the body weight, and we selected subjects that could withstand that. So not all were subjected to 10%. Some of them were like 9.5 or so. But in practical terms, the perturbation magnitude was the same for all the subjects, and they were selected specifically to be able to withstand those perturbations. So before enroll them in the study, we first tested them. So the experimental conditions were the same for all subjects.
Okay.
Okay. So we can move on to the last part. Okay. So now we come to the dynamic balance training in post-stroke subjects. So I will now show you in the video what our device is capable of, what kind of training it can be provided. So here we see, this is my colleague, so control subject walking in the device, looking into the virtual reality environment. And you can see now that the machine can apply constant forces from the back, simulating walking downhill, and from the front simulating walking uphill, and this is matched with the virtual reality scenery. And now I will show you here on this video also, we can apply with this machine, we can also apply constant forces and constant moments. So in straight walking there are no forces, so during the overground walking. Now I'm turning to the left, and now the machine is applying force to the right, so emulating the centrifugal force, and also the clockwise moment is applied, so that I need to exert counterclockwise moment in order to emulate turning during overground walking. Okay, in interest of time, I will skip now, turn to the right. You can imagine what would be there. And here is the training of the post-stroke subject, one of the post-stroke subjects in this environment. So what the subject can see here, the center of mass, who needs to be somewhere in the middle of the workspace of the robot. And then he walks uphill and downhill, makes turns, and depending on, there are some banana peels. And when he steps on the banana peel, the machine applies perturbation in the direction left, right, inward, outward, and so on. But depending on the particular deficiencies, the subjects we tailor pretty specific training program for them. So another thing that could be done with the BART machine is the symmetry training. What you see here is the center of pressure and movement, which has for control subjects, it's perfectly symmetrical butterfly. Here is the center of mass movement, but you can see for the hemiparetic subject, it's not so perfectly aligned. And what we can do, for example, here, if the subject, so with the right-hand sided paresis, when a person enters the stance with the right leg, we apply push. But now this push is not in order to evoke perturbation response. The magnitude is much smaller, but the duration is a bit longer. And what that means is that paretic subjects, hemiparetic subjects tend to spend little time on their paretic leg. So when they enter the stance, what would typically therapists do, they would grab them for the pelvis and then they would hold them a little bit on that leg and saying to them, okay, please spend some more time on your right side. And now this can be done by the machine. So the machine does that instead of human therapists. And at the same time, this can be combined with clockwise rotation. And here we see, this is in one subject who exhibited this kind of asymmetry. So here, what we see here is the center of mass and center of pressure in the frontal plane, in the sagittal plane, and the vertical component of ground reaction force. Here you can see clearly that he spends much more time on the left side as on the right side. And after the 30 sessions of, let's half an hour lasting session for 30 training sessions, we can see this kind of improvement in the symmetry of walking. So this is one example. Another example that we did with different subjects is to perform push-off training. So so if we talk about the right-sided hemiparetic subjects, so when this subject entered the stance with the left leg, this is the period of gait cycle where the push-off from the right leg is required. And at that time, for a period of time, there was a backward directed push and downward directed push, which facilitated response from the right side. And another very useful way of facilitating that is also the symmetry training from before. So if you instead of this kind of intervention, you use the push to the right, you get similar results. And what you see here is this is the assessment with the Vicon system of overground walking. So the solid line shows different kinematic goniograms, the moments, and the ankle power. So what you see is that after 30 sessions of training like this, what we see here is the significant improvement in the push-off of the paretic lower extremity in this particular subjects. Also, there is increase in the walking speed. So this comparison is not the same walking speeds, but still this is quite substantial increase in ankle power. And also the anterior posterior ground reaction force component, you can see differences. It's also improvement in the knee flexion and so on. So the gait improved quite considerably with this kind of training. And then at the end, the feasibility of perturbed balance training. So here I will show you, this is a case study. Here we will show you a situation, so the gentleman who is right-sided hemiparetic subject. And here you see his response to the perturbation to the left when entering the stance with the left leg. And you can see that the response is quite similar to the one in the control subject in the study before. This is from multiple views. And now we will see the perturbation occurring on the right side. When the perturbation occurs on the right side, so on the hemiparetic side, you see the stepping response. So what you see here is that it is the left leg that makes a cross step and the perturbation is counter-reacted only here. You can also notice quite substantially bigger displacement of central mass. So this is if you look now at the center of pressure, center of mass after the perturbation. So this is the situation before. So clearly we can see nothing much is going on in the instance period and everything is done with the cross step. And after the 30, actually here, we had a quite prolonged training. So there were 60 sessions of training. And after 16 sessions, we can see that some of the instance response is kicking in. There is also, this is combined with stepping response. Compared to the control subject, this is quite substantial improvement. And if we look into we also looked into the muscle responses in the EMGs. So here we have gluteus maximus, gluteus medius, and so on. And if we see what was going on before, you can see that on the paretic side, muscles barely reacted to the perturbation. And after this 60th training session, we can clearly see a response in gluteus maximus, gluteus medius, gluteus gastrocnemius, both gastrocnemius, soleus. So not only the hip response, but also we can see that there is also the appropriate modulation of muscles which primarily act in the anterior posterior direction, and this is quite similar to the control subject. And if now we see now we will see the responses after the training, after 60 training session. So this was unperturbed walking before, and now the perturbed walking. So this is to the left. This is the same or similar as to the before training, and now this is to the right. And you can see the difference, right? So to the left, and now again to the right. You can see that the subject learned to respond in a way that you saw the healthy control before. Okay, so to summarize or to conclude this presentation, what we can say is the dynamic balancing responses following perturbations during slow walking are quite complex. We saw that it's a combination of responses, and also here in the last few slides, that most of the muscles of lower extremities are involved, and this involvement is such to control, to quite precisely control angular momenta in frontal and sagittal plane. And dynamic balancing responses in post-stroke subjects are quite demanding as well. Some of the post-stroke subjects are capable, those that are considered to be ambulatory are capable to generate adequate responses, and the others are not. And we have also shown with several case studies that the symmetry training, push-up training, and perturbation-based training are feasible, and they show effectiveness potential. And this is something that we are working on currently to do it in more subjects and show that to a larger extent, on a greater scale. So thank you very much for your attention. And now, please, I see that there are some more questions for this last part, and then we can have a general discussion. So thank you.
Yeah, thanks, Professor Zlatko, for such an informative presentation. I'm sure attendees will benefit from this talk, and they will be having many questions. So people can start posting their questions in the Q&A box. So meanwhile, panelists can ask few questions if they have. Yeah.
Okay.
So we have one question from a attendee. So he asks, is it possible to obtain pressure distribution of the foot on the BART device?
No. What we measure is just the instantaneous center of pressure and the ground reaction forces. So we do not measure the pressure distribution. But I mean, if you use the separate system that could measure that, then I guess that it is possible. But we didn't do that.
So I have a question. So I mean, first of all, yeah, very interesting talk, I think, to see on the dynamic balance of stroke patient. I think that was quite interesting. So just to, I think, understand, I think you have already conducted these experiments. So are you, have you conducted like the long-term or kind of, let's say, after multiple session training for such dynamic balance?
Yes, well, these last slides, these were after 30 sessions. There were 30 sessions and 60 sessions. So they were quite long-lasting sessions.
I see.
What we didn't do that in very many subjects. So these are all case studies so far. So we just recently started to do it in more subjects. But unfortunately, Corona actually stopped that. So we ended up with a study on perturbation-based training where we have like 5 additional cases, which we will try to publish quite soon. But let's see when we are able to resume with these studies, because now it's quite difficult to do this.
Yeah, completely agree. So I think this is very interesting aspect that applying perturbation, which are kind of coming for a fraction of the gait cycle, rather than distributed throughout the gait pattern, you actually presented results that showed significant improvement in the ground force reaction, as well as the strategy the stroke patient were taking on the paretic side. I mean,
yes.
It's not a question. It was just a very observation. I think.
Yes,
Quite
I may add to that of course this depends on the rehabilitation potential of each individual. It may be well the case that you can apply like 60 sessions of this training and there will be none result.
Mm-hmm.
So it really, what is important is to identify people for whom you think that they have a potential, and you can see that after a couple of sessions already. But we also have experienced that there were people that didn't have that potential, and actually we had some people, you know, that underwent 30 training sessions and nothing has changed because they simply didn't have that rehabilitation potential left. So this should be taken, it's not like, you know, this will happen with every subject, but this means that people that are able to develop this kind of, or to progress in that, then it would be pity not to expose them to this such kind of training, because clearly they could benefit. Now it's a question whether or not they could benefit from some other type of training. But we know from there are quite a substantial body of literature has piled so far on the perturbation-based training, and this literature all says that people do, of course, in general, or they improve more. But what we would like to bring in additionally is that perturbation-based training should be also focused, should be targeted to the, you know, to the deficiencies which are subject-specific. It doesn't really make sense if you have a subject who is quite capable of counteracting perturbations in the forward, backward directions, but he has a problems with the outward directed perturbations, then clearly it makes much more sense to subject this subject to more outward directed perturbations, because he could then gain more from such a training.
Yeah, thank you. Krishna, you have.
May I? Excellent talk. Very interesting to note the set of experiments. Initially, I was like intrigued how this research in healthy participants translates to rehabilitation type of applications, which you have very well answered in the second half. But I have one, coming from a cognitive science, fundamental neuroscience perspective, that when a person feels an internal sense of imbalance, right? So how you sort of counteract that? Because your talk has focused mostly on trying to help people to get the normal gait, but how the elephant standing on one thing, or the people walking on a hedge, you're trying to balance, right?
Right. A very good question. Thank you for this question. Yes, you're right. Dynamic balancing responses are very context specific, right? So what I didn't include in this talk today is actually our latest project, which is on self-induced perturbations. And the self-induced perturbations basically are perturbations where instead of using the BART device, what you do, you project next step location for a subject. So for example, subject enters stance with his left leg, and at that moment he gets projection of his next right step location. So then subject first needs to, there is a cognitive process involved. He first needs to understand that, okay, now next step that I need to take is more to forward or more to the right or more to the left. So we saw in the responses part of the delay which is associated with cognitive processing. Because only after this period of time lapsed, we could see change in the movement of the swinging leg, trying to accommodate to the next target. And when that happens, so when you step with your next right step, for example, to the next location, then what happens is that you created the center of pressure, center of mass situation, which represents now mechanical perturbation. So here we have a cognitive perturbation and then followed by mechanical perturbation. And this is something what I think you are most interested in. And now we did that in control healthy subjects, and we already saw that there are certain directions which are much more manageable than the others. We then tested that in some of the amputee subjects, because we first wanted to say, okay, we would like to have people that are cognitively sound, because in a lot of hemiparetic subjects, the cognitive part may also be a problem, right? But we will try that also in them. So this kind of study is, I think, is very interesting in terms of in what way, and then that now coming back to your original question, which was, you know, how you could cope with the internal misinterpretation. So where there is actually no perturbation, but you just, you know, you figure it out wrongly. Well, maybe this kind of self-induced perturbations could be trigger, you know, to situations like that. Because also, you know, when healthy controls are manipulated in a way where sort of one of the sensory system is manipulated such that you, for some period of time, you don't understand that actually you are in disbalance. And then after you realize that, then there is a biomechanical response, right? So, so maybe this is one thing which is also quite prospectful in terms of stroke rehabilitation when it comes to these internal sources of imbalances. I hope I somehow
very
answered.
interesting. Very interesting way of how you study this internal aspects by introducing a cognitive. I have another question. So if, you know, in the virtual reality task, when you're trying to train somebody to turn left or right, walk downhill and uphill, so you're trying to help this person. But also again, in normal people, what happens is you have this predictive ability that, and therefore you do not watch where your footstep falls. So in the patients, do you see that they are more deliberate and are they watching their footsteps or are they using their predictive ability to say, okay, I'm going to get a right turn in the road, so I'm going to adjust my gait pattern accordingly?
Yeah. Most of the patients, they tend to look on their legs, on their feet, to see where they place their steps, which indicates that their internal representation is somehow impaired, so that they cannot rely to their proprioception as much as controlled subjects do. So they rely more on visual information. But we saw in this case studies of training, we saw that people actually tend to abandon this looking on the feet more and more. And but not again, but like my response to Vinet's question before, again, it depends on the person. You have people that will be always looking at their feet, no matter what. Some of them will discontinue doing that. But we see both.
Very interesting. Thank you.
You're welcome.
So are there any more questions, Sanjeevi?
Oh, yeah. So I have a small question. So for as we move towards the subject-specific interventions, so for how we decide which plane we have to apply the force, like is it the perturbation should be applied on frontal plane or sagittal plane, like how we decide that, or how to choose a combination depending on subject?
Okay, so what we do, we actually in the beginning we subject them to all kinds of perturbations, all different directions, all different phases of the gait cycle. So instance in the gait cycle when the perturbation occurs, and then we see already by visual observation which perturbations are most difficult. Also, we ask, we also clearly we measure that as well. We can see it also from the objective measurements. But in the first, let's say, introductory session, we do that. We do the whole session like 20 minutes or as much as the subject is capable of tolerating this. And then at the end, we see which perturbations, which timings, and so on are most difficult ones. And then when we tailor subject-specific program, we then do not only apply only these perturbations, because then you would get sort of habituation effect, but we tend to have more of those perturbations in, but they are still randomly distributed among the, let's say, whole block of perturbations.
So, and I have one more small query. So in one of your slides, you mentioned you kind of putting a VR environment, and you mentioned that you're asking subject to take a right turn, left turn, or let's say if you are creating such environment that he might step on a banana peel, so on. So is it part of assessing that, how he reacts, or it's a separate task?
No, this is done before. This is done before, not in this virtual reality augmented environment. This environment was developed because otherwise you can imagine 60 training sessions where you only look into 2 ellipses is boring, even though it's perturbation based. So we like to combine these different aspects. And then also there are different paths which are generated so that people really do not repeat their walking environment, so that it's the level of engagement is high. But I'm not sure if I was clear enough. We do not ask people to make turns or go uphill or downhill. In the virtual reality, this happens, and the BART forces follow that in synchrony. So we do not tell to subject nothing. We don't tell anything to subject. But subject, when they go in virtual reality to the left turn, for example, they will also experience centrifugal force working to the right and clockwise directed torque. So they will automatically adapt to that. They need then to make a lean more to the left and so on. And they are quite capable of doing this. But there are no verbal, if you like, instructions.
Yeah, thanks.
You're welcome.
So thank you so much, Professor Zlatko. A very quick question, just adding to what Professor Krishna was asking. Have you also studied any kind of interaction that the patients are having when you are having certain groups that are trained with the kind of virtual reality and few with the overground walking with force perturbations? Or in all the cases you have tested or trained those paretic patients with virtual reality?
No, the patient that underwent 60 training sessions, he first underwent 30 training sessions in the, let's say, boring environment. So in the environment where he was just instructed to maintain the position of center of mass in the middle of the green ellipse or in the middle of the robot workspace. And also, so part of the training was perturbation-based training, part of the training was symmetry training, where the cognitive feedback was, well, where there was a biofeedback showing the time spent on the left and right leg and so on. So this was for 30 training sessions.
Okay.
And 30 training sessions was okay. But then next 30 sessions, they were in virtual reality. So, so basically what we do, the training session lasts for approximately half of an hour. So 10 minutes of this time is done the symmetry training, just providing a feedback on that, so with no virtual reality. And then there are 2 more 10-minute sessions in the virtual reality environment with perturbations and so on.
Okay. Okay. So it's a cumulative of all those trainings. Yeah.
Yeah.
Thanks. So
You're welcome.
Yeah. Thank you so much for such a wonderful talk on how force perturbation could be used in these rehabilitation modalities. I hope everyone would have enjoyed the session. And if anyone has any query left, they can mail us at hcr.lab@iitjn.ac.in. So that's all for today's session, and we hope to see you all in the next upcoming sessions. We will be posting the updates on our website and mailing you guys about those things. So thank you so much and have a nice day. Thank you, Professor Zlatko.
Thank you. Thank you very much.
Thank you, Professor Zlatko. I think it went little over than 1 hour, but I think it was a wonderful session.
Okay. Thank you.